Yeah, let's talk about properties of line integrals, right? So what are the properties? Yep, so here if you so here line integral of a vector field, right? Vector field, right? This is a vector now. So orientation is very important when you yeah, very important. But previous one, line integral of a scalar field, orientation doesn't matter. I think yeah, doesn't matter. Yeah, when you compute the line integral of vector field, orientation is very important. If the orientation is reversed, then your tangent vector, tangent vector is changed to negative t. Yeah, that's the thing. Yeah. So when we change the orientation, yeah, so let's say this is C, yeah, this side. When you change the orientation, minus C other way, minus C is other way down, right? This is minus C. When you change the orientation, what happened to line integral? Line integral remains the same, but you have to put minus sign. Why? So this tangential vector is changed to opposite sign of that. Yeah. So that's why f dot t ds is equal to minus yeah this one here. When you reverse when your orientation is reversed, yeah, don't forget to put first compute the line integral of the vector field along C, then put minus sign. For instance, here. So what is the work done by the vector force field when you move opposite direction, when you move from here to there, not from here to there, from upper to below, right? So you have this solution, then how do you find other way around? Yeah, just put negative 3 pi over 4, yeah. All right. So this is yeah, so you can rearrange the way of the equation here like this here. So this is the conversion of this is the conversion. What is this here? Yeah, you can write this one this way, yeah, and this way, yeah, you can write. So this is same with, yeah, so yeah, this is f dot dr by dt. So here r is a vector. Yeah, you can cross this one. That's why you have this f dot dr. That is dr dot. So those are notations. Yeah. So then you can put dt. Yeah, you can rearrange if your force is in this way. You can simplify very easily. Right? Yeah, you can take the dot product. Yeah. And if you want to simplify this, useful. And this will do this in this form. Or you can put this dt, then put dt here. Yeah. Can rearrange the equation. Yeah. These are very simple. Alright, just rearrange the equation here. You can rearrange this to put dt and put another duty. Rearrange the equation, and if you know, yeah, this is x of t, y of t, and you can find first derivative. Very easily put that in, and your y is equal to this. Yeah, plug that in. Yeah, simplify. Yeah, very easy. Yeah, fine. Yeah. And you can do various computation. These are very simple to understand. Yeah, you will do some questions, then you can understand. You can rearrange what the form you need, right? Okay, simple. Yeah. So you. All right. Now let's go a piecewise mode. Yeah. So here we go. Yep. So let's discuss simple curves. Yeah. So we are always talking about smooth paths, right? So let's discuss this path is simple. What do you, yeah, what does it mean? Yep. So if the path is simple, you don't see these kind of, yeah, so these kind of self intersection intersections, you don't see. This is not simple, right? And this is not close. If the path is close, so starting point and the ending point are the same. This is a closed path. Yeah, this is a closed path. Okay, we understand that. And what is this simple? Simple means you don't, if you don't have these self intersection parts. If you look at this path is simple. So you don't see any self intersection parts in this path, right? So this is called a simple path, but it is not closed. If it is closed, closed, then we say this is a simple closed path. This is not simple because we can see. Yeah, so these are two-dimensional paths, right? This is a simple two-dimensional path, two-dimensional closed path, not simple one, but close, right? Close. This is not close and not simple. Right. Yeah, simple. Yeah, so for simple closed path, at the end, the initial and the ending point. Yeah, so vector at the initial and the ending point are the same. Vectors at the initial and ending point are the same, but you don't, so in between you don't see any intersections. In between you don't have any intersections, right? Yeah, this is nicely, nice, simple closed path. Yeah, now this is the open one, right? Okay, so this is how we denote the line integral of a scalar function over the simple closed path. This notation, we use this notation to denote the line integral of f over a simple closed path. So this is the line integral of a vector value function over a simple closed path, right? This is a line integral of a scalar value function over a simple path, right? Yeah, let's discuss these domains, simply connected domains, regions or domains, right? So what does it mean, right? So so what does it mean? So let's consider this domain or region, right? So let's consider any simple closed curve. So this can be shrunk here. This can be shrunk to a point continuously in this region. This can be shrunk to a point continuously in this region. So here, simply say you don't have any holes in this region, in this domain, no holes, no separation. So this is this is called simply connected region. If you don't have any holes like this, so if you have a hole like this, you cannot you cannot shrink this close simple closed curve to a point continuously because of this hole, right? If there is no hole, you can continuously shrink this closed path to a point very easily, right? So this type of domain is called, these type of domains are called simply connected domain. So let's assume F, your field is defined on this domain, simply connected domain. Your field, remember your field, this is your field. Let's assume your field is defined. This is another concept. Here we go conservative on domain. All right, so let's define your field. Is defined. Let's consider the field. Your vector field is defined on these kind of nicely simply connected domain. In this domain you don't have any holes, no separations like this. Disconnected and no holes, right? So your F is defined on this region, let's assume, right? Okay, and let's assume that field is conservative. Why? Okay, let's assume it is conservative. We know that, remember, we know that if it is conservative, there exists a scalar value function such that if you see, let's assume F is conservative defined on a simply connected domain like this, and F is, since F is conservative, this force is conservative, there exists a scalar value function such that gradient of F. So this is the scalar value function, simple F, right? Such that gradient of F is equal to your force, right? Your vector field F. All right. So let's consider a closed path. This is a closed path. Like this here. This is a closed path. So I will put starting point and ending point on this closed path. This is A, B. I will put 2 points. I will mark 2 points. On this path. So I will move an object from A to B. From over this path. I will label this path is C1 and this path is C2, right? So if I move this an object from A to B, so what is the work done under this force? What is the work done under this force? Work done TR. So over this path. Let's say C1. So we know that F is conservative, then there exists a function, simple yes, the lowercase f such that f is equal to gradient. Yeah, I can replace that. Here, C1 grad of f because f is conservative one. Dot r is vector. Yeah. Yeah. So this is that, and yeah. So if yeah. All right. Let's move your object from A to B over this path. Then you get, yeah, let's move that. Yeah, what am I saying? Let me check. All right. Okay. Right. All right. Look at this. All right. Okay. This one. Because it is conservative. Let me go to this. Yep. What is this? Yep. Yeah. A, B, this path is C1, and we take another path, C2. Yeah, so field is F, which is conservative. That means there exists a scale value function F such that F is equal to gradient of F. Okay. And what is the work done? Work done when you move a particle from A to B along C1. Yeah, this is the work done. Yeah, C F dot dr. Yeah, because this is conservative, then F is equal to this. Conservative. Gradient F dot dr. Okay. Okay. All right. Okay. This is same with what is gradient? Remember gradient F with respect to x, gradient F with respect to y, and so on and so forth. Right? If you have higher dimensions. Dotted with, yeah, you can rearrange this dt, dotted with dx over dt, dy over dt, comma d space dz over dt, right? Yeah, let me find. So I have done dx dt, dy dt, dz dt, and here we have dt, right? This term dt, last term, right? Yep. So let's simplify this. Partial f with respect to x, dx dt. Yeah, expand this. Yeah, I simplify this dot plus partial f with respect to y, dy dt. Partial f with respect to z, d, z dt, and you have dt here and integral, right? Yeah, so here f is a function of x, y, z, and x, y, z are functions of t. So you can use chain rule, right? Chain rule. So df by dt, because there is only one t, one variable. F depends only t. That's why df by dt, which is same with f partial derivative of f with respect to x times, yeah, partial. Why I am saying partial? Because here we have three variables, that's why it is partial, times here dx by dy, because here we don't have any other variables, only t. Yeah, so that's why this is dx by dt. And we can write other two as well. Partial f with respect to y. Yeah, let's write that. And this one, yeah, plus partial f with respect to y, dy dt. Yep. Again, partial of f with respect to z times dz by dt. Partial f with respect to z dz by dt. Yeah, so this is same with, so this one, right? This one I will write here. So I write in terms of t right here now, right? So t variable changing from, let's say the corresponding t value is a, right? Corresponding t value here is b, right? So t changing from a to b. So I could write, yeah, this one is same with df by dt, df by dt, and here we have a dt, yeah, dt close this off. So this is same with f evaluated at b minus, I will say evaluated at f evaluated at b minus f evaluated at a. Yeah. So if your field is conservative, so when you move a particle from A to B, the work done on that particle under this conservative field along this curve does not depend on the path. It depends on the starting point and the ending point. If the starting point and the ending points are the same, so that means if you have a closed curve, starting point and the ending point are the same, what can you say about the work done? What can you say about the work done? Yep. If the starting point and the ending point are the same, this value is same with that, then the work done of a conservative field, work done of the particle under conservative field is equal to what? What is the work done? Work done is 0. Yeah, nice result. If you have a simple path, closed path, because it is closed, starting point and the ending point are the same, right? So if you move this particle under this conservative field, so the work done when you move this particle along this closed path, you get zero. Yeah, you get zero. Yeah, you get zero work done. And the other important thing is if you move this particle from A to B, right, under this conservative field, so the work done does not depend on the path, but it depends on the starting point and the ending point. That's all. So that is a good result. Yep. So that's why. So if you have a conservative field, so path, this path does not, path, you can take any path. Yeah. So this path, you get the same work done under conservative field, right? Only for conservative fields. Nice fields, right? Conservative fields. When you go and you consider this, but the ending point is this, you get the same work done. So work done when you move the particle over this path is the same with work done of the particle when you move along this. So work done does not depend on the path, but it depends on the starting and ending point. This is a nice result. This is valid only for conservative fields. If the field is conservative defined on a simply connected domain, so integral of f 0, then so the integral of f does not depend on the path. It depends on the starting point and the ending point. That's all. Depend on initial point and the terminal point of the curve. Yeah, that's the very nice result. Yeah, this one. So yeah, so how? Yeah. So any questions? Yeah, it's a nice. Just yeah, f is a 3D. Yeah, f is a vector field from where to where? R3 to R3. Yep, R3. Yep. So this is the domain because these are polynomial. It is defined for all R3, right? So R3 is your domain. If you consider R3, it is a simply connected domain. It is a simply connected domain. Like this, you don't have any holes or anything. If you consider it is a simply connected domain. Okay, R3 is a simply connected domain. Okay, now if you show the curl of that field is equal to, or if this, so because this is, so we know that this is a simply connected domain. If you show this field is irrotational, that means, so this one is equal to 0. If this field is irrotational, then definitely this guy is equal to gradient of some function. If you show this field is irrotational on this domain, because this domain is simply connected, no holes, right? because these are polynomials, right? Polynomials in x, y, and z. Yep. So this, so f is defined for whole R3. So if you show, so f is irrotational, that means the curl of f is equal to 0 everywhere, then this field is irrotational. That means f is equal to gradient of some scalar function. Okay, so show that this is irrotational and mention this is simply connected domain, and f is defined. F is an irrotational field on simply connected domain. Because of that, then there exists a function f such that, so f is equal to gradient of f. That is how we show that it is simply connected, right? It is simply connected. Now, how do we find that scalar potential? So this is called scalar potential. So how do you find scalar potential? Let's find. Okay, this field is conservative. So how do you show that? First, mention the domain. Domain is R3, right? Because it has only x, y, and z, and these are polynomials. So f is defined on entire R3. R3 is a simply connected domain, right? And if you show gradient of or curl of f, or if you show f is irrotational everywhere, then you can say there exists, then this is equal to gradient of some function, I will say f. So x. So how do you find f then? So we can show this is irrotational. Just show now. We can show it is conservative by proving this is irrotational everywhere. First show this one, right? Then you can say because this is simply connected and this field is irrotational, therefore this is conservative. Then there exists a function such that scalar function such that that's gradient of that scalar function is equal to this field. Then then how do you find this simple f? We can find that. So this what's the time? Okay. So I'm recording this. So first component, this one is same with the first component of that. That means first component, this one is same with the first component of that. What is the first component? Gradient of partial of f with respect to x, first component. And second component of this is partial of f with respect to y, which is same with the second component. And third component of this is partial of f with respect to z, which is same with this. Okay, we have this, right? Then consider this one first, and we can integrate this. Can integrate d with respect to x, and you have to put arbitrary constant. This time, because this is partial, the arbitrary, here we get an arbitrary function g. So that function depends on other variables. Other variables are, so here we integrate with respect to x. So other variables are y and z, right? When you integrate this, you get this. Yeah, all right. So you have this. Okay, now you can obtain this one by differentiating with respect to y. Right hand side is equal to this, right? Yeah, so partial of respect to z with respect to y, partial of respect to y. So this side is equal to this side, this one. So let me write that down, x z minus e x sine y, which is same with, partial of this with respect to y, ex, sine y negative. This is x z. This is partial, with respect to y g. Yeah, so you can cross this off, and partially when you, so 0 is equal to, 0, where's that? Cross this off, so partial, when you differentiate g with respect to y partially, you get 0. That means g does not depend on y, and g is a strictly function of z, only z goes like this. So g is a function of z only, not y. So f is equal to e to the x cos, here this one and this term and this one, and we can use this one. We can partially differentiate f with respect to z. Let's do this. Partially with respect to z, both sides. Partially z, this becomes 0. This becomes x, y. This becomes h prime. The right hand side, and partial of f with respect to z is, this one, z plus xy, and you can close this off, of course. And here we have an h contains only one variable. Very easy. Z equals h prime. Integrate this because this is ordinary. So when you integrate ordinary, 1, you have to add a constant. So not here we are not partially integrating, here ordinary integrating. That's why you add a constant, right? So z squared over 2 plus constant, and put this one into here. So then you get f. F is this one plus this one plus your h is equal to this. So this is the potential function, right? Makes sense. So next time I will